Okay, we took a little break from the problem because it's getting complicated, and I wanted to give you a little breather. But now let's go back and finish it off. Okay, let's go back to the notepad here. All right, here we are again. So let's take advantage of symmetry now, and let's look for even parity solutions. Meaning that psi of x should be equal to psi of minus x, okay? And when we're done with this, then we'll go find the odd parity solutions. And it makes sense to do this because each of those problems is much easier than the general problem is, although the general problem is solvable too. All right, now, if we have if we know the solution is even parity, then we can simplify things quite a bit in the following way. In that case, we know that the wave function in region 2 should have even parity as well. Now, the cosine function has even parity, yay. But the sine function does not. It has odd parity. Its value at positive values of x and negative values of x have opposite sign. And there's no way that a sine function can contribute to an even parity solution. So that means we know that for the even parity states, that b must be 0, okay? The sine function doesn't contribute to the even parity states. So for the even parity states, we know that b must be equal to 0, and we know something else. We know that because the wave function must have the same value on the right and left sides of the well, we know that a must be equal to d. Okay? So that simplifies things. Now, instead of 1, 2, 3, 4 coefficients that we have to solve for, now we only have 2. Okay? Very good. Okay. So we know that psi in region 2 now can just be written as c times cosine kx. And psi in region 1 or region 3 are simple as well. In fact, let me write down psi in region 3, and this can be written as d e to the minus alpha x. Okay? Okay, now we can start to use our boundary conditions. So boundary condition 1 tells me that the amplitude of the wave function psi 2 of x equals L over 2 must equal psi 3 of x equals L over 2. Okay? And so that means that c times cosine of k L over 2 must equal d times e to the minus alpha k L over 2. All right? That's our first equation. Our second boundary condition uses the slope. So the slope of the wave function also has to be continuous at the boundary. And this gives us a second equation. So the first derivative of the psi 2 is minus k times c times sine of L over 2 times k. And this has to equal the first derivative of psi 3 evaluated at that point, which is minus alpha times d times e to the minus alpha L over 2. So this is the second equation. Okay? Now we can combine these equations in the following way. Let's just take the ratio of them. Let's take the ratio of the second equation to the first equation and see what we get. Then when we do that, we have minus k times sine L over 2k divided by cosine L over 2k. Notice that the factor c cancels out. And this has to equal minus alpha times e to the minus alpha L over 2 divided by e to the minus alpha L over 2 again. Okay? Very good. And you can see that the function on the right-hand side simplifies. The exponential functions cancel. And the term on the left side can be written more simply as well. Sine over cosine is just tangent. And we have k times tangent KL over 2 is equal to alpha. Okay? Or finally, tangent KL over 2 is equal to alpha over k. No automatic perfect square, but there's our solution. All right. Okay, now we've got some kind of solution. Let's see what it means. What it means is that the wave functions we used, cosine-like in the well, decaying exponential outside of the well, that they, A, solve Schrodinger's equation in each region, and B, they match up properly, provided that this is true, okay? So there are only certain values of alpha and k that will work, right? And what this really is it's an equation for the energy of the state. It doesn't look like it, but if you think about it, it is, because k and alpha are both determined only by the energy. In fact, if we want, we could rewrite this equation in a different form. We could write it as tangent of KL over 2. So that's square root of 2m times L over 2h bar, all of that times e, times square root of e. And that has to be equal to alpha over k, which evaluates to square root of u0 divided by e minus 1. Okay? Now I've written that second equation just to show you that both sides of the equation we've just written only depend on one value, one unknown, and that's the energy of the state. Okay? So this is really an equation for the energy of the state. The only issue is that it's a very difficult equation to solve analytically, because the energy is in a tangent function on one side, and you see the form on the other side. In fact, this is an example of what's called a transcendental equation. It can't be solved analytically, but it can be solved. It has to be solved numerically, okay? Here, let's take a look at what those solutions, at how that works, okay? And then we'll come back to this problem. 1 second.